Okay, so for this week, or for today, which is week 7, Tuesday, we're going to do stresses on combined loading. So last week, if we look into last week's notes, okay, so last week we spoke about, is this last week? No, this one is last week. So last week, we look at a structure that has compound loading or combined loading. So the structure is under axial stress, under shearing stress, and under bending stress. Okay, now the bending stress is also inducing a normal stress. So for today, we're going to look at a different structure now. Okay, so now some of you have seen this structure before. You say, hey, I've seen this before somewhere. Indeed, you have. So where you have seen this is you have seen this on week 1. Okay, where I did my introduction. So week 1, I did my introduction on asking you, like, giving you the layout of this course, what is expected of you. Okay, so for the past 6 weeks, you've been through 18 hours of lectures at least. And then finally, now we are able to analyze a structure that is shown in this figure down here. So we're going to do detailed calculation now. Okay, we're going to do detailed calculation, and we're also going to go into detailed analysis. Okay, right. So that's my main aim today. Okay, to teach you how to calculate stresses uh, of a compound loaded structure. Okay, and then we go from there. Anyone, any question? No. Okay. So this is the structure that you're seeing now. Okay, and then the structure is under 4 forces. Okay, so you see 4 forces are applied to the structure. So where are the 4 forces? You have 100 kilonewton, 8 kilonewton, 8 kilonewton, and 25 kilonewton. Okay. By the way, all these figures can be downloaded on Avenue to Learn. So we want to determine the principal stresses and maximum shearing stress. Okay, so I don't need you to worry about principal stress and maximum shearing stress yet. I have not taught yet. But what I want specifically to do is to find the stress state at point A and to find the stress state at point B. So we look over here, right? We look at where is stress A, or element A. Okay, so A over here, you see a square down there. That's where element A is. Over here, this is where element B is. Okay. So if we look at a cross-sectional view, this is your element A location, and this is your element B location. Okay. So now this structure is under has the structure configuration of Y200 and X41.7. So what that means is you look at a handbook. Okay, you look at a geometry from the handbook. Now this you can find on your textbook on the very last few pages. Okay, you will have all this data, and this is on appendix C. So this is known as white flange shape that designate the W. Okay, so we are looking at W241.7. So W241.7. So I'm going to highlight this section. So this is 41.7. So this is the data that we'll be using, this entire data. Right. So when you look at this entire data, right, it will tell you that what cross-sectional area you have, okay, the depth. Now, by now, all of us should know what's a flange and what's a web, if some of you forgot. So this is known as this is usually classified as our flange. And this is usually classified as our web. Okay. So you're given a flange width and thickness. Okay, so they have BF and TF, and you can relate the BF and you can relate the TF. And then you have web thickness. Okay. And then what is also given is in your x-axis and your y-axis, what is our second moment of area? Okay. our x s over x or sy, which I will talk about later on. That is to deal with bending moment. And then we have radius of gyration. Now this we will use in our last chapter of this course, which is buckling. Okay, so we are not necessary, we don't need the Rx and Ry yet for now. That is based on the radius of gyration. So now we have that information. So we're given that information and we want to find stresses at point A and stresses at point B. Okay. So again, like what I highlight, 3D problem, 2D world. Okay, our paper is 2D. So before we go on, we have to relate how this transformation over here, okay, is related to our 3D. Now, is important. I mean, it's not a must, but if you can, the transformation over here, as you can see, okay, the transformation over here, ideally, you want the transformation to be similar over here. You can see your X is in horizontal, your Y is on what? Vertical. Okay, so this transformation, when it's X and Y, it is a good practice that is the same on the handbook and on your analysis. Okay. If not, you just have to flip around. Okay, you just get a bit confusing. So let's not get. So if we look at our structure now, okay, relative to our structure, so we know that this is going to be our X. All right. So this direction is our X, and then this direction is our Y. Okay. So we have X, we have our Y, and using right hand rule, right? So this is our X, this is our Y, and using the right hand rule, this will be your Z. Okay, so based on the right hand rule. Right, so there are two formulas that we're going to use now. Okay, so we know that whatever we're going to find based on axial loading. So there are two things that we know. So based on axial loading, and bending moment, right? Based on these two, we know that we're going to find our stress in the what? In the Z direction. Okay. Sorry, our normal stress are all going to be in the Z direction for this case, based on this configuration. So we know that this will be equal to PZ divided by A. So this is due to axial loading. Then we have plus by mx over ixx multiplied by y plus by my over iyy multiplied by z. Okay, and these are due to your bending moment. Okay. Sorry, this is not this is x, and this is due to bending moment. Right, so we have done this maybe 2 to 3 weeks ago. Okay, you have to recap all of them to do this problem. So that is your bending moment. So that is for your axial load and your bending moment based on this configuration. What I want to highlight is we are all, for this configuration, we're going to calculate the normal stresses done in the X direction. Okay, then we are going to look at shear. Okay, so our shear, depending on the orientation, there's only two shear over here. So now we look at shearing. So shearing will be, you have shear in the X direction over Iyy multiplied by Qy divided by T. So you have to be careful down here, okay? Or your shear can be Vy over Ixx, first moment of area about x-axis multiplied by T. Okay, so you have to be really, really cautious down here. As I mentioned before, in terms of moment, when it's mx, when it's mx, right? I do apologize. When it's mx, right? You use ixx. When it's my, you use iyy for bending moment. Whereas for shear, when you have vx, you use iyy. When you have vy, you use what? Ixx. You have to somehow remember to flip them around. Okay, is just the opposite. The shearing is just the opposite from bending moment. Just about it. Okay. Right. So this is the formula. So some of you will ask me, Eugene, uh, is this some of you will ask me now, right? Some of you are curious. What is this? Is this in XY or what or XZ direction? Don't worry about that yet. Okay, later on when we go into detail, we know what we are calculating on. Okay, right. So now let's look at the structure and let's break them down. Okay, break them down into a 2D problem. Okay, so I'm going to draw my transformation now. So this is the transformation. So if you can do a screen capture on this, so when we analyze, or I will copy every time when we need this diagram. Okay, right. So we are going to look at this diagram. So we're going to look at in the let me copy first in a small. I will go to another page to copy so I can get a smaller one so you can see better. Right. Okay. Right. So now we're going to view this in a. We're going to view this now. Okay. In a. So I'm going to have my x, and this is my z. Right. So I'm going to view z, and then this will be my rotation about y. Okay. That's my rotation about y. So when I take that view. Okay, so when we look at the view, we draw the cross section out. Oh, sorry, we draw the load. Okay, so I'm going to sketch. So this is what we will see, right? The bottom part. And like what I mentioned before, we have to identify the first thing that we have to do. Some of you might have forgotten it. We have to define. We have to know where the position of neutral axis is. So this is the position of the neutral axis. Pardon me. Okay. So this is the position of our neutral axis. Okay, so this axis is our neutral axis. Is what's important for us. Then a good practice is to sketch out your element. Okay, so from here we can view that this is your element A. Label them, and with this view, your element B is just a straight line, right? So this is your element B. Okay, so that is your element. I better follow what the book says. If it's small b, I'll use small b. Right. So from here, we're going to put in our forces. Okay, we're going to add in our forces. So our forces, we have one force coming down, and this is at 100 kilonewton. Okay, and then you have a force that's going inwards, and this is running at 25 kilonewton. And then you have 8 kilonewton, and this is going to be twice. Okay, so the first thing we do, we analyze it. So remember what I mentioned in the lecture last week. Only do not analyze, right? Just a recap. Do not analyze the dots and the what? Cross. Okay. Don't analyze the dot and the cross, just analyze those arrows. So there's only two things that you have to analyze here. Is the 100 kilonewton and the 2 of the 80 kilonewton. So from here, we know that PZ, right? There's going to be an axial load of 100 kilonewton. So we write down here, PZ is equal to 100 times 10 to the power 3